Hi Year 12, welcome to this week's introduction videos. We're going to start some work on differentiation. So I think this is where the course begins to get interesting, but also a little bit challenging. And we're going to look at sort of a very, very important practical application of limits. So I'm going to introduce you to the idea of differential calculus. Okay, so you're going to understand what a derivative is, be able to understand derivatives from first principles, be able to work out the derivative of a simple polynomial. Okay, in a few weeks we'll look at some more complex functions and how to differentiate them. We're going to be able to work out higher order derivatives, and we're going to understand some basic applications such as using differentiation to find maximum and minimum points and equations of tangents and normals and things like that. Okay, if none of that makes sense, don't worry, you haven't learnt it yet. So, just a little starter question here. Maybe stop your video and have a little go at it. Okay, so hopefully you've done that. So this says Eileen is driving from Amsterdam to Zurich. This graph shows the distance travelled against time. So very basic distance time graph. It says, did Eileen travel at a constant speed? Explain your answer. Well, no. Obviously not travelled at a constant speed because it's a curve, it's not a straight line. If you want to represent a constant speed, then you would be going at a straight line, and hopefully what you understand is that the shallower the gradient, so let's say pick a point here where the gradient is quite shallow, the slower Eileen is going. So say here the gradient is higher, so she's going faster at that point. So all we want to do is then say find Eileen's average speed for the first 5 hours. So that's easy. You just go to this point here and you start from 0, 0. So for that 5 hours you connect a straight line, and that will tell us the average speed. Speed equals distance over time. So the distance travelled is 300. Over the time, 5 hours, so it's 60 kilometers per hour. Okay, so it's almost like drawing a chord between the 2 points. What about the final 2 hours? Final 5 hours, sorry. Well, the final 5 hours is from here to here. So again, we draw like a chord between the 2 points because we're only looking at the average. So the time for that is the same. Speed equals distance over time. So the time is still 5, but this time the distance travelled is 500. And so we were travelling at 100 kilometers per hour for that period on average. Okay, that's what we were doing on average. However, everything we're going to be doing for probably the rest of the course, is we're not interested in what the average speed is, or what we call the average rate of change, the average change in your distance with respect to time. What we're looking at is what we call the instantaneous change in distance with respect to time. So we're looking at knowing, well, how fast was I going here? And hopefully you can see that whatever this gradient of this tangent is the same as the gradient of the curve at that point. So we can use tangents to work it out. Okay, so like here we're going a little bit slower because the tangent at that place, that particular time, is shallower. So we can work out the gradient of the tangent, then we work out the instantaneous speed at that particular time. So this is what differential calculus is all about. It's instantaneous rates of change. Okay? So I hope that makes sense. Now, let's say we want to find out what the gradient is doing of a certain function. So I'm just going to draw a random function. Okay? Any function will do. Doesn't really matter what it looks like. I think I'm going to draw a cubic. Okay, so maybe it's going to be something like this. Okay, so I'm just going to call this y equals f of x. Yeah, now what you notice is that there is not one gradient to this function because it's a curve. okay? The gradient is changing all of the time. So we can kind of work out what it's going to look like. At the moment, this is y and this is x. What I'm going to do instead, in green, so let me just change the colours there so I don't confuse you. So here I'm plotting y against x. What I'm going to do now is I'm going to plot what I call dy dx against x. So dy dx represents the gradient. So I'm going to plot what the gradient is at certain points. Now, let's just get red. Well, let's just look at tangent here. Well, I don't know exactly what the gradient is, but I do know it's quite large and positive. So I'm going to plot a point here that's quite large and positive. Notice that what happens as I sort of go up, the gradient is still positive, but it's not as positive before. So say at this point here, my gradient is less positive. It's still positive, but it's not as positive as before. In fact, what I'm going to do, I'm going to do it in green, and I'm going to just say it's, say, down here somewhere. Okay? So it's positive, but not as positive before. Then notice what happens here. At this point here, the gradient turns 0. So gradient value is 0 there, so I've got to plot on my y-axis as 0. And then I'm getting a ton of negative gradients. Okay, like this point here, negative, negative, until it returns again to 0. Okay, so it's sort of doing this. Negative, negative, back to 0. And then what I get is a gradient is increasing. I mean, I meant if it's cubic, it would sort of go like that. And it continues to increase forever. Okay, so I'm just getting now a bunch of positive gradients. So the green function is what I call my gradient function. So that gradient function will allow us to work out what the gradient is of the original function at any particular point. So that's what differential calculus is. It's finding out what the gradient function is of a function. Okay? So, bit of notation here for you. There are two ways of representing a gradient function with a notation. So general function obviously is y equals f of x. So you can represent a function here. This is what we call Newtonian notation. Okay, and this is what we call Leibniz notation. Okay, basically named after the two mathematicians that sort of did it this way. And so with the gradient function, we're looking at dy dx. What that is basically saying is what is the change in y with respect to a change in x. Or the Leibniz notation, we call it f prime x. So that's just with a little dash there, f prime x. I'd like you to be able to use and recognise both types of notation. Okay, Leibniz notation in particular I find helpful for efficiency, and perhaps Newtonian notation perhaps is a bit better for understanding. Okay, but you need to be able to use both. Now, what I'm going to do is I'm going to try and teach you how to find out what the gradient function is from first principles. So in order to do that, I'm going to use my friend Desmos. But just to clarify what I'm actually trying to do, I am going to try and find out what the gradient of this curve is. What is the gradient of this curve at the point 416? So what I'm trying to do really is I'm trying to find out what's the gradient of this tangent here. Okay. So one way of estimating the answer is to pick a different point. So we've got a point here. Let's pick a different point here. Okay. Now what I could do is, let's choose a different colour. I could work out what the gradient of this orange line is instead. Okay? How do I do that? Well, let's just let's just say that this is my x value, and the x value of the point I've picked over here is some amount further away. So I'm just going to call it x plus h, okay? It's at 6, but I didn't have to pick 6. I could have picked anywhere I like. So the x value of the point is 4, and then I'm moving this point some amount away from the original point. So that distance we're going to call h, sorry. So that distance is h. So now how do I actually find out what the gradient of this this orange line is? Well, you know, it's rise over run. Should know that from GCSE. So what is that? Well, what we know is if this is x value, then its y value is f of x. Okay? By the way, I should have told you that this is just the function y equals x squared. Okay? So if this has an x value of f of x, then this point here has a value, well, it has x plus h, and so the y value is f of x plus h. Okay? I hope that makes sense. So this red point here has this coordinate, we're talking in general terms, and this point here has this coordinate. Okay, x plus h, f of x plus h. Okay, so what is the gradient of this function? Well, it's going to be the change in y, which is f of x plus h minus f of x, and then it's going to be divided by the change in x. Well, that's just the distance h. Okay, so this is what we'll just call it g for the gradient function for the time being. So I hope that formula makes sense. Let me just delete some stuff now so that we can clear the decks. Okay. Right, now, so bear that formula in mind. What I'm going to do now is I'm going to go to Desmos, and we're going to have a look what happens if we actually do it. So, Desmos, where are you? Okay, so here's Desmos. So here is my function. My function is, here we go, y equals, d is 1, so it's just y equals x squared. Okay, and what I'm trying to find out is the gradient of this dotted tangent here, because that will be the same as the gradient of the curve at that point. Okay, now, so what I did is I put in a point some amount to the right of that function, and then I connect that up with a line, and I say, okay, what is the gradient of the black line? Now, you'll notice that the gradient of the black line is not the same as the gradient of the tangent. Okay, they're different. So the black line gives me an estimate of the dotted line, but it is not a very good estimate. Okay, it's not a very good estimate at all. But how can I make my estimate a bit better? Well, that's pretty easy to do. All I need to do is move my point closer to the original point and watch my line get closer and closer and closer to what the actual gradient is. Okay? Now, look what happens when I actually arrive at the point. The black line actually disappears. I want to think about why does the black line disappear. It then comes back again, and my estimate gets worse and worse and worse and worse. So what you'll see is my black line is getting better and better and better and better and better and better, and then it disappears, and then it gets worse and worse and worse and worse. When it's actually on the point, it would be perfect estimate, but it's disappeared. Why is that the case? Okay, have a think about it. Stop the video and have a think. Okay, well let's actually do what we've done. Okay, let's actually do it with the numbers that we've got. So the function is y equals x squared. So what we're saying is let's go for x plus 2h squared. That is my y value at this point, minus x squared. That is my x value at this point. Okay? We know it's 4, but we can put that in later when we've actually worked out. Divided by h at that, which is the change in x, right? Okay, now, what I'm going to do now is expand and simplify this. So I'm going to get x squared plus 2hx plus h squared minus x squared, all divided by h. Notice the x squareds cancel away, so I'm going to end up with h squared plus 2hx all over h. That is the general formula for my gradient for this particular function. Okay? Now, what you'll notice is, as I move my point down the curve, then what I'm doing is I'm making h go towards 0. So what if I let h be equal to 0? Well, I'm going to get 0 squared plus 2 times 0 times x, all divided by 0, which equals 0 divided by 0. That is why the black line disappeared. You ended up with an indeterminate form, okay? 0 divided by 0. But I taught you last week, if you get something like that, 0 divided by 0, then there is no value of that function, but there will be a limit of that function, okay? So instead of trying to find out what the value of this is at h equals 0, what we're going to do is we're going to find the limit as x tends to 0 of h squared plus 2hx all over h. So remember what I said, you do your direct substitution, which we already done. We found out it was 0 divided by 0. So when you get 0 divided by 0, what you need to do is some work to eliminate the discontinuity, okay? Which we can easily do because we can factor the top. That will be h times h plus 2x divided by h, okay? And that is how I managed to cancel away the discontinuity. So now I get 2x plus h, okay? And as x tends to 0 for that function, sorry, as h tends to 0, I've written that wrong. That should be as h tends to 0, because h is moving towards nothing, not x, as h tends to 0. H tends to 0, we just end up with 2x for this function, okay? So what I know is that the gradient function, I'm going to call it dy dx, or f prime x, for this function, y equals x squared, is 2x. So now what I can do is I can use that function to work out what the gradient is anywhere along this curve. Well, what I know is if x equals 4, then since the gradient function is 2x, then f prime of 4, the gradient function at the point 4, is equal to 8. Okay? So, let's just zoom out. What I know is that the gradient of the dotted line here is 8. Okay, the gradient of that dotted line is 8. And if the gradient of that dotted line is 8, then the gradient of the curve at that point is also 8, because they are the same thing. Okay? Right, hope that makes sense. There's more videos to come, but let me know if you want me to clarify any of that. Okay?